Let's get started with today's pre-lab lecture. So in distillation experiment 3D, we're going to be looking at the separation of 2-methylpentane and cyclohexane. Note, in your lab manual provides you both the boiling point and refractive index. You can also find the boiling point and refractive index from literature sources as well. Now, as we notice, if we compare the boiling point of 2-methylpentane and cyclohexane, the difference in boiling point is less than 30 degrees. This is a key signpost in terms of what technique we need to apply. A simple distillation would likely not be able to efficiently separate our 2-methylpentane from our cyclohexane and collect initial fractions with a pretty relatively high purity. So in order to separate these two compounds, which have a relatively small difference in boiling point, what we're going to do is we're going to utilize fractional distillation. Now, compared to what we did previously in our distillation lab, where we were essentially utilizing one-plate distillations, where we have our reaction pot, we establish a single liquid vapor equilibrium as we move up the column, and in turn, we collect fractions. This is considered functionally a single plate distillation. Now, of course, each time we redistill, we add another theoretical plate. That's what we did previously in our first two distillation laboratories. Now, in fractional distillation, utilizing a spinning band column, so a spinning band column is designed in a way, it's either designed where we have a Teflon band that rotates, that is embedded in our column and embedded in the neck of our distillation column. And the main benefit of a spinning band column is that at each site along the spinning band column, we can establish a new liquid vapor equilibrium. So each site allows for a liquid to vapor equilibrium, and that in turn leads to increased theoretical plates. As each time we establish a liquid vapor equilibrium along our spinning band, we're able to further enrich our vapor in this case, the lower boiling component. So the spinning band allows multiple sites for liquid vapor equilibration, and in turn, it allows successive enrichment of our vapor across each theoretical plate as we move up the column. Now, compared to a simple distillation, which would be considered a one-plate distillation, a spinning band column allows you to run one distillation, which has approximately 6 or 7 theoretical plates. Now, of course, you make a small concession in terms of column holdup, but overall, a spinning band column is utilized in fractional distillation in order to achieve a separation with a greater number of theoretical plates, as we have a greater number of sites for us to establish a liquid vapor equilibrium. So, as we move up the column, we establish a liquid vapor equilibrium at multiple nucleation sites, and each time the vapor gets successively more enriched in our lower boiling component or in one of our mixture components, depending on the temperature that you're at. Does that idea make sense? Does everyone see how a spinning band column functions and why it achieves a greater number of theoretical plates? Any questions on this idea? Okay, so to keep going, if we think about our classic vapor pressure curves, so for example, just to draw it out, so we have our temperature in degrees Celsius as a function of x, which is your mole fraction, right? And for a mixture, we can look at the mole fraction present in the liquid and the vapor. So for example, we'd have our vapor phase and our liquid phase composition curve. So the top will be our vapor, the bottom will be our liquid. And if we have a wide difference in boiling point, let me draw this a little bit wider. So this is our vapor. And the bottom curve is our liquid, right? So suppose that we start with a 50-50 mixture. So let's suppose that we start with a 50-50 mixture. So we start somewhere around here. A single vaporization and condensation cycle, so this is one cycle, constitutes one theoretical plate. So if we establish a liquid vapor equilibrium, we notice that our vapor is substantially more enriched in our component X, which is our lower boiling component. So as we notice, after one distillation cycle, if we look at the liquid vapor equilibrium, our vapor is enriched in our lower boiling component. Now, we can actually quantify using these liquid vapor composition curves the exact composition of our distillate. And as we notice, our distillate composition after one distillation is has a mole fraction of around 0.9 for our mole fraction. So approximately 90% of the sample in terms of moles consists of our lower boiling component after a distillation cycle. Does this idea look familiar? So each distillation and condensation cycle is a theoretical plate. If we have a large difference in boiling point, if we compare our liquid and vapor composition, our vapor is substantially enriched in our lower boiling component. If we allow our vapor to condense, we end up with our distillate liquid that is highly enriched in our lower boiling component. Does that idea make sense? Does that idea look familiar to everyone from the distillation discussion? Can I get some confirmation in the chat that this idea looks familiar to everyone? Perfect. Now, if we have a large difference in boiling points, as we've noted from this liquid vapor composition curve, we can achieve a pretty efficient separation using just one plate. However, if our boiling point difference is very small and the higher and lower boiling components have a very small difference in boiling point, we require more plates in order to achieve an efficient separation. I'd really like you to take a look at your lab manual, and I'd like you to compare the liquid vapor composition curves for hexanes and toluene versus 2-methylpentane and cyclohexane. So I'd like you to compare how these two liquid vapor composition curves look like. And as we've noted in this pre-lab lecture, when there's a small difference in boiling point between our low boiling and high boiling component, we in turn require more theoretical plates in order to achieve an efficient separation. We need more liquid vapor equilibration cycles in order to generate a pure distillate. Does that idea make sense? Perfect. So what are we actually doing in this lab? What are we doing in a practical sense? So we're trying to separate a mixture of 2-methylpentane and cyclohexane. We are looking at a 1-to-1 mixture. And our goal is to separate this 1-to-1 mixture using fractional distillation using a spinning band column. So as we discussed in fractional distillation, what we are functionally doing in fractional distillation is we are taking we're taking almost a snapshot of a portion of our liquid vapor curve. So what do I mean by that? So if we have our liquid and we have our vapor, the vapor has a defined composition at a given temperature range. So what we're doing is we are taking a fraction, for example, fraction 1, over a given temperature range, and in turn, our fraction 1 will have a small sliver of different compositions based on the temperature range that you collect your fraction. So for example, you collect over a temperature range T1 to T2, and in turn, your vapor and your collected distillate has a composition X1 to X2. So fraction 1, the first fraction that we are going to collect, is enriched in 2-methylpentane. It has a boiling point of around 60 degrees Celsius. It won't be exactly 60 degrees because this mixture contains a little bit of our higher boiling cyclohexane component. Just like in any fractional distillation, we'll collect a mixed fraction. This mixed fraction has a boiling point from 61 to 79 degrees Celsius, and we'll be able to determine the exact composition of that mixture using collected physical property data. Finally, we'll collect a third fraction that is enriched in cyclohexane. When you watch the video, you're going to need to make sure you accurately record the temperature range. Does this make sense so far? Does this idea make sense so far? How collection of fraction functions in terms of the theory and practically what we're doing in the first part of this lab. Okay, then we are going to measure the mass of each fraction. By measuring the mass of each fraction, we can calculate the percent recovery. And in turn, we can also begin to look at the mass percentage and raw mass of each mixture component isolated. Once we have the mass of each fraction, we're going to record the refractive index of each fraction to calculate the volume fraction. I just can't emphasize this enough. The refractive index equation gives us the volume fraction. Okay? So in your lab manual, there's an equation that specifies that for a mixture of cyclohexane and 2-methylpentane, the volume fraction of 2-methylpentane, is equal to the following number minus the refractive index over the following pairs of numbers. This equation is derived from the refractive index of each of your mixture components, and it assumes that refractive index is linear with volume fraction. Okay? You've actually used a similar equation in earlier laboratories to estimate the volume fraction in our earlier distillations. Okay, so you're going to measure the refractive index, plug it into this equation, and it will provide you the volume fraction of 2-methylpentane, assuming refractive index is linear with volume fraction. Okay? Now, once we have the volume fraction, we have a table on page 138 of our lab manual that provides a relationship between the number of theoretical plates and the volume fraction. Now, this graph does not work well above 7 or more theoretical plates. It becomes hard to tell when you get to a really, really, really pure sample what the exact number of theoretical plates is. So what you're going to do is you're going to measure the volume fraction using this equation. And after you get your calculated volume fraction, you're going to take it to the table. And if, for example, you have a volume fraction of 0.9 for your 2-methyl pentane, you'd estimate that your number of theoretical plates would be around 6.5. Now, of course, theoretical plates is a whole number, so you'd round this to 7. And so from the refractive index, we can estimate the number of theoretical plates. Does that make sense to everyone? Now, why am I mentioning the number 7 a lot, or around 6 to 7? Why would that number come up for a number of theoretical plates? When we thought about our earlier discussion of spinning band columns and the approximate number of theoretical plates for a spinning band column, would anyone like to answer? What is the approximate number of theoretical plates for a typical spinning band distillation column? Roughly, around. What is the approximate number of theoretical plates for a typical spinning band column? What does everyone think? 6 to 7, exactly. So you'd expect from your volume fractions, you'd expect a calculated number of theoretical plates to be somewhere around 6 to 7. Yep. Okay. So this should all look familiar for the most part from our distillation labs. What we're now going to do is we're going to add and apply a powerful technique that we've learned in gas chromatography. So what we're going to do is we're going to analyze our samples via GC, fraction 1, fraction 2, and fraction 3. We are going to compare the calculated volume fractions to the peak-to-peak area ratios observed via GC. Now, what I really want to emphasize is that these peak-to-peak ratios determined via GC provide us an estimate for the mass-to-mass ratio or the mass percentage. So if you want to actually perform an accurate and more direct comparison, you need to convert the mass percentage obtained via GC into the volume percentage. Okay, so we're going to analyze our samples via GC. We're going to compare and calculate our peak area ratios. And we're going to take this one step further. For each of our analyzed fractions, we're going to calculate the retention time, peak width, and theoretical plates observed for the GC. And then we're going to compare the height equivalent theoretical plates for the GC column and the theoretical plates observed for the spinning band column. So essentially, you're going to compare the number of theoretical plates for a GC versus the number of theoretical plates for a spinning band column. Does anyone have a guess, using our chemical theory that we've talked about for GC and for fractional distillation, which column has the greatest number of theoretical plates? A gas chromatography column or a spinning band column? What would you guess would be the column with the greatest number of theoretical plates? The GC. The GC would win out. The gas chromatography column would win out 100%. Gas chromatography columns have anywhere from 300 up to potentially even 1,000 theoretical plates, while a spinning band column has around 6 to 7. So that is partially why when you look at and you try to separate these mixture components via gas chromatography, we're able to achieve a pretty dramatic separation between our two components. Okay, now to unpack how we analyze our samples via gas chromatography and how we analyze our detector outputs. First, let's talk a little bit about a little refresher. So this will be a refresher course on analyzing peaks. So here's an example of a worked peak. So first, what we do is we look for the inflection points, which are the points when our line changes in terms of slope. We identify our inflection points and then we draw our tangent lines. Our tangent lines, when they cross the x-axis, will give us our our start and end of our peak. And we can calculate then our peak width using our 2 times at the start and end of our peak. Additionally, when our 2 tangent lines meet, that gives us the retention time, which is very close to the center of our peak. So we can record the peak width and record the retention time. Does this look familiar to everyone in terms of how to work up and analyze a peak from our detector output? Does this kind of peak analysis look identical to that which we did in the gas chromatography lab? And don't worry, I'll do a worked example with a printout that we'd observe from the lab from one of my other runs. Okay, so once we have the peak width and retention time, we can calculate the number of theoretical plates using the following equation. This number of theoretical plates is what you compare to the spinning band column. As always, we can look at the exact number of height equivalent theoretical plates for the column that we used by taking the length over the number of theoretical plates. And then what you can do is you can then compare this HETP to the previous HETP found for the GC lab. With a side note that you need to make sure to check which column was used. So since we often are using the same instruments, right, we would expect the height equivalent theoretical plates to be relatively consistent between experiments, assuming similar temperature profiles, right? And since we use the same gas chromatography instruments in the GC labs, we can calculate our HETP and then compare to what we've seen in previous experiments. Does that make sense? Does that idea make sense to everyone? Okay, so from your GC detector output, so from your raw data, we can calculate the percent recovery and the mass over mass percent. This is from isolated masses for each fraction. We can then calculate, using the peak area, the approximate area over area percent. Now, there are 2 methods of calculating peak area, both of which are commonly used by integration algorithms and commonly used practically in analyzing and working up gas chromatograms. The first of which, you take your area by calculating 1/2 times the peak width times the height. The other method is to identify the width at half height, and the area is defined as the width at half height times the height. There's another method that I'd like to call 2B, where you take your peak and you literally cut it out and you weigh the peaks. Although that method is relatively, has often been applied in older instruments and before we actually had detailed computer analysis of our peaks using integration software. But you can just as easily get the peak ratios and the approximate peak area by actually cutting out your gas chromatograms and weighing the peaks. Okay, so once you have the areas, you can calculate the area over area percent, which is roughly equal to the mass over mass percent. Okay? You'll do that for each of your fractions. Then you'll assign the identity of each peak using the retention time and physical properties collected. Okay, so that is a full overview of Lab 3D distillation. Any questions on this laboratory as of right now? So I'd like to show you